Okay, class. Today I wanted to do a video going over homework problem. This was from the last homework set. I believe it was homework set 6. So the problem is actually 10-97, if you guys remember. And I think these are it's a Navier-Stokes approximation, but it has to deal with boundary layers. And since I didn't really post, I posted myself simulating a laminar boundary layer. But I haven't really posted a lecture specifically going into boundary layers. So this will kind of serve as that too. But there was a question during the live stream that I did last class session, which would have been April. What's today? Today's April 12th, so just about 3 days ago. I think April 8th or April 9th would have been the day. There was a question about going over homework 1097. So you can go ahead and look it up. We have the solutions posted, but I just wanted to give you a little bit of a feedback as to how I would solve it or how it's solved. Let me read the problem. It says a streamwise velocity component of a steady incompressible laminar flat plate boundary layer thickness delta is approximated by the simple linear expression. So we have this is a common delta symbol here. It's a lowercase d in Greek. This stands for basically a boundary layer. But specifically the boundary layer having to do with the velocity. So having to do with velocity as a function of x. How that is, well, a function of x and y. But let me go ahead and draw what we're talking about here. So I'm going to go ahead and draw, I'll just use different colors, see if it's okay. So we're going to go ahead and show you a flat plate like that. And then I'm going to draw the boundary layer. So what we have is a flow of fluid going in this direction like this. And we'll just give that the capital V for the velocity of the fluid. And then what's going to happen, you're going to develop a boundary layer. I'll give it this nice rust color. And so you're going to have a boundary layer that looks like that. Now, do you remember at the surface we have a zero slip condition, so this is as a function of x. And then there is a component that's a function of y that way, so we're going to say this is the y direction. And now what we have here is the boundary layer. So the velocity profile will look something like this. Change the color here. So what's going to happen is that you have zero slip at the surface there, and you're going to have velocity going from 0 to some maximum here, and then it just does this. It goes straight up, and basically it's constant after that. So what you have is, if you go from 0, there's a function that gives us when we get to the boundary layer, and now you just have you have your straight flow this way. This is what's happening here. We're going to call this u of x is basically this representation, and up here past the brown boundary layer, this is just equal to v, which is this basically this v here. It's just there's a constant velocity here at the onset of the flat plate, and then because of no slip, you're going to go from some 0 to the maximum value. And so here, this part that's under the curve here, well, that's represented by a function that's given to us. And that function is equal to, it's going to say u is equal, hold on a second, that's pretty bad, u. Okay, u is equal to, and it's basically capital U, y, and then divided by the boundary layer. Okay, so I haven't talked to you about the boundary layer yet, but the boundary layer, for example, at Uh, well, here's X, right? So let's go ahead and say X. Here's X. So the boundary layer height, I'm going to go ahead and go back to another color, it's this height here. It's basically from the flat surface of the plate to the brown line. And that's the boundary layer here. Let me do a little bit better job. That's basically delta, right? And that's a function of X. But so I'm going to go ahead and just say defined at X. So this is what our X component is. So there, that thickness of that brown surface, or the brown layer here, is called what we call the delta boundary layer, and it's basically a velocity profile. Basically says once you go above that brown layer, the velocity is constant, and it's basically equal to the velocity at the entrance where it came over the plate. All right, so that's what we're saying, is that above here, we know that above the brown line, the velocity is just v, and when we say u, this is the same thing as saying capital U. Usually that's the capital U is what we give for velocity. We call it the free velocity, or the velocity far away from the plate, and that's the same thing as the velocity that comes in at the entrance. So what we're saying is that this parabola here is this function here. All right, now what we got to do is we got to calculate two things. We got to calculate the displacement boundary layer. I'm just going to say boundary layer, and then we have to, so we just call that delta star or delta asterisk, and this one is called the momentum layer. All right, so what the delta star layer is, it's basically how should I say it? So I'm going to go over here and say, so to talk about the delta star layer, so you have this boundary layer, you have the flat surface here, you have this layer that we're going to call delta, and you have the velocity here that comes in here, and so we've seen this at the center here. You go from 0 to some value here, and then you just go straight up like that. So this is our velocity profile. So this is delta of x. So basically it's a function of x. Kind of looks like a square root function. All right, so now what the displacement layer is, I'm going to draw these streamlines here. So what's happening is as fresh fluid is coming in this way, this boundary layer is going to cause it to deflect up like this and continue that way. You ever see the streamlines like in the car commercials where they have like a certain white gas that's going over the front of the car, and then the streamlines do this bump up, right? So that bump up, so for example, let's say we want to measure it here. So let me go ahead and draw a different color here to demonstrate what that bump up is. So from this point right before it bumps up, I'm going to draw a line like that, right? And so at this point here, for example, we're going to call that delta star, and that's basically the distance that it bumped up because of this boundary layer. In other words, if this boundary layer wasn't there, if the effect wasn't there, this streamline will continue to go horizontal. But because there is a boundary layer there, it actually forces all the other streamlines to go up. And so that is what the delta star is. And so we call that the displacement. I'll just say it's the displacement boundary layer. Now the momentum boundary layer is a little harder to explain, and that one is basically it has to do with the boundary layer causing some momentum shift that affects the shear stress on the plate. And that basically is just, it can be modeled as just another, like a thinner, it's less than the velocity boundary layer, the delta, the black one, and it's it's given some value theta, and it's theta sub x, right? So it would be as a function of x as well, like that. And so again, that's the momentum boundary layer, and it has to do with the momentum changes caused by the boundary layer, and it can be again modeled as a thinner. It's always less than the velocity boundary layer. Just keep that in mind. So these are the things that we're trying to calculate. All right. So let's go ahead and open a new page here. Call this one. All right. So now, all right. So let's go ahead and let's. So what we have is, we have a way of calculating the displacement boundary layer, and that's looking at this integral here. The integral from 0 to infinity of 1 minus little u over big U, or capital U, dy. All right, so that's, and then that's how we find the displacement. And the good thing is we basically have a function that's given to us. We have two ways. Again, if I was going to go back and I wonder if I can go open what we were just watching here.